Is the screen visible? Thank you. Okay, so in the last session, we have discussed the singly linked list and a few of the cases like how we have to insert and remove the elements or the nodes in the singly linked list. Now, with the help of the same structure, we can implement the stack program as well as the circular queue program. Now, with the array, we have discussed that how to implement a circular queue. There was a formula wherein if we take the mod of the current index plus one value, mod with the size of the array, then we get the exact next index, right? So that formula we have seen. Let's say front, we want to increase the front. If we do front plus one modulus with the size of array, then it will automatically give the next index. If the front is right now, if let's say front is 0, if we add it with the 1, then it will be 1 mod. Let's say there are 4 elements in the array. Let's say there are 4 elements in the array. Maybe array is the bigger one in this case. 0, 1, 2, 3, 4, and 5. So there are total 6 elements. If I say 1 mod 6, or automatically I'll go to the sixth one more location, that is the index will come here, and when you reach the last index, that is 5, if you take mod 6, you will come back to the 0th index. This is how we can implement the circular queue with the help of the array, right? Now with the linked list, implementing a queue is a even simple task, because what kind of structure we have implemented, the node is of this style, wherein the first section is utilized for the data. Here we have data in the node. So this is, let's say, data. And here we have a pointer to the next element, right? Now, if we are, let's say I have many such nodes available with me. Now, there are 4 nodes in the list, and we know that there will be a chaining of these nodes, right? Now, what we have to do is the last node should point back to the address of the first node. So let's say this is the start of the linked list. This is the start of the linked list. If the last node is pointing to the start of the linked list, earlier in the earlier session, what I've said is this last pointer, this last address should point to null. That is what we have done. The last element that we create in the linked list was pointing to the null value. That is nothing. It was indicating the end of the linked list. But if we start pointing from the last element to the very first element, ultimately you have kind of a circular queue index or queue kind of a story. That is, you will start with the first index, you will travel in the list, and as you hit to the last index, the next value, the formula to travel the linked list will be, let's say we are traveling and we get the t index. So t is equal to t is next. So this is how we will start. We will say that here we will say that the t will copy the value from the start. He will copy the value from the start, and then to travel to the next node, we will apply this formula. T is equal to t is next. In the older case, if t is next, is equal to null, it means this is the last node. This is the last node in the linked list. We can conclude that this is the last node in the list. Okay, and now here, as the last node is pointing to the first element, you will never reach to this condition. In the case of circular linked list, you will never reach this case, because whichever new node you want to add in the at the end of the list, that new node will obviously point to the first address, because you are creating a circular list. So how you will conclude that you have traveled the entire list? So here we can say that if t is equal to t is equal to start, if t is equal to start, means travel is complete. Okay, are you with me? Are you with me? Yes, okay. So if this condition match, if this condition gets satisfied, that means you have traveled the entire queue. And can anyone tell me what is the other thing with this queue? If let's say we are not implementing a circular queue, let's say if we are having a simple queue, if we are having a simple queue, Omparth, I guess your mic is on unmute mode, muted. Let's say this is what I have right now, and I am saying this is my queue. Let's say I am saying this is my queue, and this will be the front, and this will be the rear. So can anyone tell me, if you compare this structure with the array list, what is the major difference? Can anyone tell me what will be the advantages of using this linked list structure compared to the array structure for implementing the simple queue? Anyone? Can anyone tell me what will be the advantage of we can eliminate elements? Okay, so this is one advantage, that we can eliminate elements. Any other? Any other? Can anyone think of any other thing? Any other advantage? You are just implementing a simple queue, not even circular queue we are not talking about. Anyone else? We can access any block. So no, with the array also we can access any block, but that is a structure. Like in the stack also we can access any block if we decide to travel through the index, but that is a limitation of a structure, and we have to follow that rule, that you can add and remove only at the top in the structure, and in the queue you can remove from the front. That means you can access only front, and you can insert only at the rear. Memory management. Can anyone, Ronali, can you please elaborate on what you mean by memory management of a queue? There are two answers in the chat. One is from three answers posted. One is posted privately, and one is to everyone. Three answers. Okay, so few students have got it correctly, right? adding. So basically, single linked list only creating at the end is actually kind of a queue operation wherein you are adding at the last, at the end of the linked list. So if we think in the terms of a traditional linked list and there is only one operation, if for our sake we assume that in our linked list there is only one creation possible, that too at the end of the linked list, then we are actually following the rule of a queue, that we are adding at the rear value, right? So there are other operations like insert in between, insert at the start, insert after, insert before kind of operations. So if we remove those operations from our linked list program, there is only one. We will keep only two operations in the linked list program. That is, we can remove only the start node. If we just put a limit that if we want to remove anything from our linked list, we can only remove the start node. So if we want to remove the start node, how we will remove it? We will simply say temp is equal to start, right? So now temp and start are pointing to the very same index. And after this, I'll say start is equal to starts next. Start is equal to starts next. So now what will happen is the start index, which is pointing to the first value, will move the location, and now the new value of the start will be here. So right now we will have still temp variable is still here, which is pointing to the first address. But now my start of the linked list has moved from the first value to the second value. Can anyone tell me, can anyone guess why I am copying the address of start into temp before moving forward? Before moving forward, can anyone tell me why we are moving forward? Why I'm copying the address of temp before moving forward? To display which element is removed, of course, because we don't want to lose previous element. So if we don't want to lose previous element, that is true when we are traveling the linked list. So we will discuss this case, why we copied the address into the start. Okay, so I'll discuss that case. But if I'm talking in terms of a memory management, there is one important point we have missing, right? So that's why I've copied the start of the start address into temp. Can anyone recall? Or can anyone relate it to the discussions that we had for our memory management session? There is some, we are reserving this memory using malloc, right guys? So we are reserving this structure memory using malloc function. This is the code for reserving the memory, malloc, right? So I've explained one point. Malloc allocates memory where the malloc memories get. Yes, now I have one answer in the chat window. To free the memory. So malloc reserves the memory on heap, and we have discussed it many times that the uh, free memory function works only with the stack. Your automatic garbage collection or automatically freeing the memory or relieving the memory from the program happens only in the case you are allocating a memory on the stack. As soon as you allocate a memory on the heap, that time the memory allocation will not be freed. So what will happen is, let me create a tree structure. Let's say this is the start node. So this is my heap structure. Now what will happen is, sorry, there was this node 1, there was this node 2, and there was this node 3. So what are these contents of these all nodes? In reality, this is the picture. So there are 3 nodes in the list, and they are not linked actually. This is the logical link that we are creating. Let's say this first node, uh, second node, and third node. There is a compartment in all 3 nodes, right? So in the first node, we have value 1. In the second node, we have value 2. And the third node, we have value 3. Suppose there is an address of first node. Let's say the 000 is the address of the first node. 001 is the address of the second node. And 000 010 is the address of the third node. So how the link is been established? In this section, you will be having the address of the second element 001. And in this section, you will be having the address of the third element 010. And the last node will not be pointing to anything. Here we will keep null. So now this linked list is formed. And in our program, through our program, what we were saying, start was holding the address. Start was holding the address 001. So once we go to the 001, that is, sorry, not 001, it's mistake. I should say 000. Start was holding 000. Once you go to the start, that is the first node, from the first node you can go to the next node by writing. So how I'll do is I'll say, if I, let's say if I write the code start is equal to starts next in the program. If I write start is equal to starts next, who is starts next? 001. So what will happen is at after this line your start will start pointing to 001. You will come here. Now, as soon as this happens, the start pointer is modified. Now, there is no way for you to recover this. So, your node, the start was here. From here, the start has shifted itself to point to the first location. Now, as soon as the start variable moved from the first location to the second location, there is no way that you can reach back to this position. So it is called as a memory leak or losing an element or losing the node from the list. Whether this node is deleted, no, node is not deleted. Just because you traveled from the first node to the next node, now you are not able to access this node. So we have to, while traveling the linked list, while traveling the linked list, going from the first node to the last node, we always take care that we never use start pointer. We never use start pointer, because if we travel using the start pointer, we will lose the first element in the linked list. And if we lose the first element in the linked list, then it's hard to recover that particular point. Right now I've traveled only one location, that is the second element. So I'm losing only one node. Let's say I have a linked list of this sort. So let's say this is the first node, and let's say I have many such nodes. And let's say we applied this formula. We applied this formula to travel the linked list. If we say start is equal to starts next, if we apply this formula while traveling the list, let me delete everything else, not required right now. So if we apply this formula, start is equal to start next, let's say what will happen is the earliest the start was pointing to the first element. From there, start will come here. From this position, the start will come to the next. Let's say you have traveled for the two times. If you call this code one more time, let's say you have traveled to the this place. So let's say we have called this code. Let's say we have called the start for the first time to come here, second time to reach the second node, and the third time to reach to the third node. Now we are from 0th node, we have traveled to the third node. Now after these three start calls, let's say this was the 0th address, this was the first, this was the second, and this was the third. Now what is the new value of the start? The new value of the start will be pointing to the third element. So start will be pointing to the third location, let's say. Now there is no way for you to reach back to the first address, because there is only one link using which we are going forward. Are you with me? So if we just use this sort of travel, then we cannot go back and access these nodes. We cannot go back and access these nodes, right? So just to make sure that we will not lose the start address of the linked list, just want to make sure that we don't want to lose the start address of the linked list, what we do is we say a temporary variable we create and we say temp is equal to start. And now we will say temp is equal to temps next. Using this, the temp will keep on traveling and you will still be in the position to go back to the first element because we are not modifying the value of start. So you will not lose the any chain in the linked list. You will just use temp variable to travel to the any next node in the queue, right? But what if you want to remove the element from the queue? That's a very simple thing. What if you want to just, let's say if you are dealing or treating this program as a queue program, what happens in the queue? You remove from the front, right? What happens in the queue? We remove from the front. So what I'll say is, instead of calling this first address as a start address, I will call the first address as a front address. Now to remove this front, I should directly write front is equal to fronts next. If I do so, the front which was earlier at the first place will travel and go to the second index. Now this first index which was earlier pointed by front and you have traveled to the next index. So now this first node cannot be accessed because you have lost this address using the second style of coding. So still in the second style of coding also we should follow this copying of a node or copying of the start address. But instead of going to in forward using the temp, we are going forward using front itself. Then why to copy this? Let's understand. So before going forward, what I'll do is I'll follow the same thing. Just I'm changing the naming style. Earlier I used to call it as a start. I am now calling it as front. So I'll say temp is equal to front. We will copy it, and now I'll say front is equal to fronts next. Now two variables are here. One is a front which is pointing to the next element, and there is other variable called as temp which is pointing to the first node. Now this is what has happened here also. So when we don't want this node, even if we have no pointer which is pointing to this particular block, even we have no pointer or a variable which is keeping the address of the first element, in this case that has happened, in this case the same thing is happening, the computer do not release this memory. In the case of C programming, this is the special case of C programming wherein this memory still is remaining allocated on the heap area. To remove this memory, we have to make a call, and that call is free and pass the pointer which is pointing to the node free temp. So here also I'll write free temp. So as soon as you execute this free temp, what happens is this memory is released from the computer space. So now after executing free temp, this memory will be erased. So that's why we still need to copy the address of front or the start while treating it as a queue. So when we are going to call this as a queue, instead of calling the first index as a start, I'll call it as a front. Are you with me? Is the concept clear? How to get a queue with the help of a linked list? If anyone have a doubt, please ask. If anyone have a doubt, you can ask. Okay, okay. So I'll create some operation, and we are going to have So Viraj, can you tell me SYC 70, what will be the value of start? What should be the value of start in this case? Viraj, in the SYC 70.
Yes, sir.
What is the value of start? What should be the value of start? What will
One.
be, huh? Viraj,
Yes, sir.
what is the value of start? Okay, SYC 73, Vinayak Patil, can you tell me what is the value of this start?
Zero, sir.
Zero.
Yes, sir.
Okay. Suyog Sabare, what is the value of start?
X0.
X0. Okay. And if I want to go to the if this is the queue and if I want to go to the next element, how you will do it? What will be the code for that? If I want to go to the X one, okay. If I want to go to the next element as in a queue, so how the code of line of codes you will write?
Temp is equal to a start
Uh,
and start is equal to starts next.
okay. And just done.
Pre-temp.
Okay. Correct. So uh, SYC 65, Mr. Vaibhav, can you tell me what will be the value pointed by rear? Where the rear will point in this case? SYC 65. Vaibhav. SYC 61, Rajeshwar Patil. What will be the value of rear in this case?
Yes, sir.
What will be the value of rear? If this is the queue, what will be the value of rear pointer? If I create a rear pointer, what it should point to?
Sir, 5.
That is the data value. What will be the value of pointer? If I create a pointer called as a rear, what should be the value of that rear pointer? If I create this as a pointer, if this is the pointer, what this pointer will be holding? Sriraj Kosge, roll number 56, SYC 56. Sriraj. SYC 46, Rahul Divse.
Sir.
Yes, what will be the value of rear? Rahul, you're on mute mode. SYC 13, Miss Asawari. What is the value of this rear? SYC 13, Miss Asawari Dikshit. Miss Saira Sandhi, SYC 02. What will be the value of this rear? Miss Saira Sandhi. Good. So many people have just joined. No problem. So Krutik, are you there? Can you tell me what will be the value of rear?
Is it X4?
Of course, it will be X4, right? If I say, if of course this has to be called as front, pointing to the front element, then it must be pointing to the X0. And if I say this is the last index, then obviously it will be pointing to the X4, right? So that is the value of rear. This is my last node, right? And what is the last node's next? Last node's next is null. The last node's x is null. So if I say x post next, is that is the null value. So using this, you can create a linked list. Sorry, not a linked list, a queue. The good part about the queue using the linked list is you are not worried about the queue is full condition. Queue might be empty if there is no node in the linked list, if the both front and rear are pointing to null indexes. So in the case of array, we picked a value called as a -1 to indicate that there is no index in the array or there is no value in the array. So in the case of a linked list, we can say that if both indexes are pointing to null, the queue is empty, right? There is no node in the queue. Unless and until these both are not pointing to null, the queue will have some element, right? Basically, they will be pointing to the same value, that is x0. In that case, there is only one node, or they will be basically pointing to two different addresses, in which case there are more than one node in the queue. And circular queue, just make sure that this last index, instead of having the null value, it will keep the address of the first element. So you will have a circular queue with the linked list. Okay, now if we have to implement a stack, that is even a simple story. Let's keep this diagram. Let me increase the size of the eraser. Yes. So let's say I am going to treat this linked list as in a stack. Can anyone tell me how you can use this as in a stack? If you want to keep this single linked list, if you want to use this single linked list to implement a stack, what will be the logic? Anyone? How you could manage it? Jatin or Ashish? Okay, just do start is equal to starts next to pop. Manage using front and rear pointers. Soampagi. Okay. So Soampagi is even giving a nicer answer. So front will be the first element in the stack and rear is pointing to the last element. So you can still manage. See, so just you have to change the name of the pointers, call the rear as a top and don't lose the address of the first element in the stack. That is the start address. And keep that element as in a top. So what I'll do is I'll still keep the copy of a start, and initially start and top will point to the same index. And as if I add a new value, I'll say the top is going forward, and I'll keep always track of top. As soon as I add a new element, if I add a new element, I'll go on saying top, right? And now if you want to remove, if I want to remove this, just drop this value of top. Just drop this value of top. Before dropping it, we have to travel till the top. So what I can do is temp is equal to start, right? And then temp is equal to temps next until what? Until what? Until temp is equal to top. So as soon as this happens, you just free the top. Free top. Are you with me? Are you with me? Yes. So this will be the kind of a simple stack program. Now there is a problem with this approach. Whatever cases we are discussing, that okay, we are managing this, we are creating a structure called as struct node, right? And in this structure, I have two parameters created. One is integer, let's say data, and then the pointer to the struct star next. This is the definition of the structure that we have created for the single linked list node. Now there is a doubly linked list, something. There is a concept of a doubly linked list. So this is a node of a singly linked list. Why we call it as a singly linked list? Because there is one pointer. There is only one pointer which is pointing. So there's only one link going from first node to the next node. And because there is only one link, we have to do this all jargon, like never lose the start address. If you lose the start address, then you will lose the number of nodes. That's the limitation. While going forward, use the temp and then hop to the next element. As soon as you reach your destination, then you can free up the null. That these all problems are because we have only one link, and that is a forward link, forward-looking link. Now, what we can do is, instead of creating a structure like this, instead of creating structure like this, if we create a structure like this, if we modify the structure definition, struct node, now what I'll do is I'll say struct node star previous integer data struct node star next. Okay, now look at this. In this earlier structure, we have only one pointer here. In this case, we have 2 points. So if to draw the imaginary diagram, how this block will look in the memory, if I have to create a visual representation of this structure node in the computer's memory, then this node will look something like this. This node will look something like this. Like you have three sections in this node. One section will be utilized to keep data, whatever data you want to store. And then here, you are having a pointer and we are calling it as next. And here also we have one pointer. We are calling this pointer as previous. Now what we can do is this pointer will point to the earlier address, the previous node, and the next will point to the next element in the list. So if we follow this style of creating a linked list, if we follow this style to create a linked list, sample linked list will look like this. Give me a minute. So I'll create some nodes. Let's say earlier link, there was only in one direction. The link was only in the one direction. Now what will happen is, if I draw a link, let's assume this link is bidirectional, that you can go from first node to the next node as well as you can come back. Okay. Now let's keep some data. Let's say this is 1, this is 2, this is 3, and this is 4. And let's assume that these nodes also have addresses. If we assume that these nodes have addresses, let's say this is the 000, this is the 001, this is 002, and let's say this is 004, then there is no one before this. So we'll say this is the null. I'll call it as start also. Now who is starts next? 001 is starts next. So I'll write here 001. But this previous link now can be used to keep pointer to the earlier element. So the previous link will point to the address of the earlier node. So I should write here 000, which is the address of the first element. Now who is 2's next? 2's next is 3. So in the 2's next session, in this section, I'll keep the address of 002. That is where I can find the next element. So if you go to the next element, that is 002, who is the previous element of 002? That is the third node. Third node's previous node is node number 2. So what is the address? 001. So in the previous link, we'll keep the address of previous node, that is 001. Same thing. Who is the next node? 004. In the 004, who is the previous node? 002. And here, there is no next node. I should say it is null. It is null, pointing to nothing. So this is somewhat the doubly linked list. Now there are two links, two pointers, first, previous, and next. So we are calling it as a doubly linked list. Are you with me? Any doubt in this? Any doubt in this doubly linked list?
सर
Yes.
सर तुम्ही लास्ट नोडला नल नाव दिलाय आणि फर्स्ट नोडला पण नल नाव दिलाय मग सर ते एकमेकाला कनेक्ट होणार नाही
नाही कळालं मला.
सो म्हणजे आता लास्ट नोडला जो 004 ऍड्रेस वाला नोड आहे लास्टला
हा
त्याला नल नाव दिलाय बरोबर मग आणि फर्स्ट नोड
इथे
हा आणि फर्स्ट
हा.
जिथं स्टार्टिंग आहे तिथं पण नल नाव दिलाय मग
बरोबर.
ते एकमेकाला कनेक्ट होणार नाहीत का म्हणजे सर्क्युलर तयार होणार नाही का ते
नाही केली आपण तर नाही होणार.
ओके
So right now we are not assigning. See, so if I want to do this, what I have to do is I have to say starts previous will point to 004. So I have to write it in program that the last elements next will be the start. Who is my last element? Last element is 004. So if I say that this 004's next is start, then only there is a link. So it will create a circular doubly linked list. So if I don't do that, I'll have a doubly linked list wherein the last node is grounded, saying that there is no next node, and the first node's previous is also grounded or saying null, saying that there is no earlier node. Okay, so this is perfectly fine. If I just attach the last node with the first node, I'll have a doubly circular list. Okay. So I have a question now. Can anyone tell me what is a major difference in the single linked list? By assuming that in the single linked list also the last node is pointing to null, and obviously there is no previous pointer, so there is nothing called as null in the first node. In the doubly linked list, the last node is pointing to null, and the first node's previous pointer will also point to null. Still, there is a significant difference in the singly linked list environment and the doubly linked list environment. Can anyone tell me what is the significant difference? Anyone? We can travel in reverse direction as well. That's perfect. We can go back. We can travel in the reverse direction. Yes, that's correct answer. Any other? No need to store previous address. Even correct. That when we are traveling, we don't need that temp and all jargon. Right. That's fine. Correct. Any other thing? No need of extra variable. Okay. Any other? Anyone? Any other? I really do not need that temp. That's correct. But what is the ultimate effect of that? What is the ultimate effect of that? So what is the ultimate more memory? Memory, of course, memory requirement of a doubly linked list is extra. So if I say 4 bytes required for the pointer, in the case of a singly linked list node, right now the memory required by the singly linked list node is 8 bytes because 4 bytes for the integer and 4 bytes for the pointer. So 8 bytes are required in the case of a struct node of singly linked list. And in the case of struct node of a doubly linked list, the memory requirement is 4 bytes for previous pointer, 4 bytes for integer, and 4 bytes for the next. So total requirement will be 12 bytes to create a node of doubly linked list. So that is correct. That memory is different. So memory requirement of a doubly linked list is more compared to the singly linked list. And in the singly list case, we are right now requiring 8 bytes. In the case of doubly linked list, we will need 12 bytes. That is correct. Okay, any other? So searching will be simpler, I guess. Yes, searching is even correct. The point I wanted to raise here is you people have given me all the answers which are concerned with what I'm asking. So ultimately you are telling me that there is no need to keep track of start. In the case of a single linked list, if I lose start, let's say if you lose this address and if you come here somewhere, then you lose the access to the earlier two elements. You can't access the earlier elements. If you just go on traveling using start and let's say you come to the third index, then these earlier two indexes you can't access. There is no way unless and until you have made a copy of start. If you have made a copy of start, you are in safe zone. If you forget to make a copy of the start node, and if you use start index itself, start variable itself to travel the list, then there is no way to go back. In the case of a doubly linked list, even if I lose the start address, if I keep the track of any of the node, if I just remember the address of the any of the node, still I'll be able to travel in the linked list. Are you with me? So in my program, at any given point of time, if I have access to memory of address of any of the node, I'll be able to travel. Suppose in the program, if I have run the program 2-3 times and I have access to this member, if I'm right now here, this is the address which I am pointing. Still, I am not worried with that I've lost earlier elements or I am going to lose the next elements. No, I can go to the earlier elements using previous pointer and can go to the next elements using the next pointer. So you still do not lose accessibility of the earlier nodes as well as the next nodes if you have just access to any of the node from the doubly linked list. Till the time you have address of any single node of a doubly linked list, you can access all the nodes, previous, next, doesn't matter where the node is. That is not the case with the single linked list. If we lose the address, those nodes are gone forever. Now you can't recover those nodes. Very simple. Sure, sure. So this is the beauty of a doubly linked list. Now we have seen a structure of creating a singly linked list. This is the sample program wherein we have created a simple two node list. Now, what I want is I want you people to explore this singly linked list program. Try to create at least insertion and create a deletion or insertion operation. At least try to create a insert operation for singly linked list. If anyone finishes with the correct menu like insert or display list, only two menu program, create a node and display the list. That will be a good thing. In the next session, we are going to implement doubly linked list in program. So this is the single linked list program. Get confident, have it, practice this, get confidence on creating a node and creating a linked list, singly linked list. And in the next theory session, I'll be demonstrating how to create a doubly linked list and how to travel, go forward and backward, a basic program. And then I'll leave the rest of the job to you people, like creating a full-fledged menu-driven program of doubly linked list. Sure? Yes. Now we can implement stack, queue, circular queue. We can implement stack, queue, circular queue with the help of singly linked list as well as with the doubly linked list. So that will be the extension. Like once we have a confidence on implementing singly linked list and doubly linked list as in a simple programs, then we have to implement a stack with the help of linked list, stack with the help of a doubly linked list, queue with the help of a linked list, queue with the help of a doubly linked list, circular queue with the help of a single linked list, circular queue with the help of a doubly linked list. That's an extension, and doubly linked list, it's a very easy stuff. With the in the case of a single linked list only, we have to make sure that we never lose a pointer. If we lose a pointer, that we are in trouble. Okay, so that is the only case we have to take care in the case of a single linked list. And also, uh, in the case of a circular queue implementation with any of these links, never forget the start. If you forget the start, you will keep on rotating in the linked list. You will never find that you have already traveled the entire queue. Let's say I'm implementing a circular queue using a linked list, and if you do implement this, like the last node is pointing to the first node, if you forget to achieve this condition that the start node is pointing to the next node, the x4 is pointing to the node x0, which was the start node, that is the next node is pointing to the start value. If you forget this condition, then you will never be able to find where is the end in the list circular. Okay, so that kind of care we have to take. So front and rear management is very important in the case of creating a circular linked list with the help of singly linked list as well as with the doubly linked list. Else we will just have some random output on the screen. So hope you people understood what is the concept of a doubly linked list. Great, great. So let's break for this session, no issues. I'll see you people in the lab sessions. You can leave the meeting.